Hi, my name is Andrea Coladangelo, and this talk is about joint work with our Sattath. I will tell you about how a classical blockchain can be combined with quantum money to achieve a payment system that enjoys the best of both worlds. In particular, this is a payment system that resolves the so-called scalability problem of blockchains. So what is the scalability problem? Well, most blockchain designs suffer from the following loosely defined problem, that the amount of resources or time required per transaction grows badly with the number of users in the system. So loosely speaking, solving this problem means keeping the amount of resources and time used per transaction approximately constant. And as an example, this problem concretely manifests itself in the long waiting times for transaction confirmations on the Bitcoin blockchain and in the limited throughput of transactions, meaning the limited number of transactions that the system can handle per second. So in the first part of this talk, I'll informally review the basics of the two main ingredients of our payment system. These are blockchains and quantum money. And I'll start with the former. So what is a blockchain? Well, you can think of a blockchain as a sequence of blocks. A sequence because you can think of them as being ordered chronologically, and each block contains information about some transactions. So how does a user add a new transaction? Well, let's say that Alice wants to pay 4 coins to Bob. At a high level, this is how she does it. She broadcasts to the whole network the transaction Alice pays 4 coins to Bob. And for the moment, we won't get into the details of how this transaction should be signed by Alice, etc. Okay, so she broadcasts it, and this transaction joins what is known as a pool of pending transactions. And every once in a while, a new block is formed containing transactions from this pool. Now, this happens via some consensus mechanism involving the users in the network. And this new block that is formed is appended to the old sequence of blocks. Okay, so let's zoom into one of the blocks. So a block contains a bunch of transactions. And what does a transaction look like? Well, informally, we expect the transaction to be specified by a number of coins being spent, who is being paid, and who is paying, and from where. However, if we are to be a bit more precise, actually, firstly, we should think of the number of coins being spent rather as coins deposited in a transaction. And these coins can be released or claimed according to some rules. Secondly, the user who is being paid is not actually specified directly, say Bob. Instead, it is specified in a slightly indirect, but much more general way, via a set of instructions phi that is decided by whoever has deposited the coins. And phi, for example, could be a circuit, and the instructions could be anyone who provides a value, call it a witness W, such that phi of W equals 1, gets to release and spend the deposited coins. So the point is that if there is a unique user who possesses a witness W, such that phi of W is equal to 1, then this user is effectively the owner of the coins deposited. So for example, if Alice is paying Bob, the circuit phi could be a circuit that requires a signature from Bob, a signature of some message, so a signature with respect to Bob's public key, which of course only Bob is able to provide. And finally, the user who is paying, so Alice, and where the coins are coming from, is specified by referencing a previous transaction. And on top of referencing this previous transaction, the user Alice also has to attach a witness that releases the coins in that previous transaction. And so one point that I want to emphasize is that in general, phi could be any set of instructions. And so such generic transactions, which are much more than just payments, can be much more than just payments. These are referred to as smart contracts. Okay, and the set of instructions could really be anything that can be specified by code. And smart contracts are what we'll be using in the rest of the talk. And now, what are the pros and cons of a blockchain? Well, the main pro is that it is decentralized, meaning it requires no bank or trusted third party. The second pro is that it is digital, obviously, in the sense that it's not like physical cash. You don't need to meet in person to exchange the physical cash. Now, the con is that a consensus mechanism is necessary. So being digital, there's nothing really preventing someone from copying a string of bits. And so there has to be a consensus mechanism that enforces the legitimacy of transactions and that prevents people from double spending. However, such consensus mechanism comes at a cost, and it typically takes time. So the consensus mechanism, which involves the users of the network, is usually the bottleneck in terms of efficiency. Okay, so now let's move to a brief overview of quantum money, which should be a bit more familiar to the audience. Now, quantum money was first proposed by Wissner around 1970. It's a form of money based on the no-cloning theorem. In a quantum money scheme, a banknote is a quantum state, which cannot be generically copied. And more precisely, a quantum money scheme is specified by a generation procedure, which we call gen, which takes as input, say, a security parameter, and outputs a quantum state, which we will refer to as the quantum banknote, and a serial number S. The scheme is also specified by a verification procedure, called it ver, which takes an alleged quantum banknote as input plus a serial number, and outputs either accept or reject. Now, what about security? A quantum money scheme is said to be secure if, given one valid banknote with serial number S, it is hard for an adversary to produce two banknotes with serial number S, which both pass verification. So basically, it's hard to counterfeit money. Now, in this talk, we'll be interested in quantum money schemes that are public key. A quantum money scheme is said to be public key if the verification procedure ver is public, meaning that it does not require any secret parameters coming from the generation procedure, say. So anyone can verify a banknote. And here is a brief state of the art of public key quantum money schemes. There are several that have been proposed. Unfortunately, none of them is secure under what we can call sort of standard computational assumptions. Recently, Peter Shor gave a talk at Simons about a scheme from learning with errors that is secure, assuming learning with errors. And so this is exciting. However, the result is still unpublished as far as I know. And here are the pros and cons of public key quantum money. Well, the first pro is that it cannot be counterfeited. This is by definition of security. Second pro is it can be potentially transferred very quickly via quantum channels or quantum teleportation, and it does not require, of course, a consensus mechanism. The con is that it requires a bank, a trusted third party, who mints the banknotes. Now, there is a stronger version of public key quantum money called quantum lightning, which is actually an essential ingredient of the payment system that I'll describe. So let me spend a few words on it. So quantum lightning was first introduced formally by Zandri. Informally, it was introduced by Lutomirski and co-authors some years earlier, and they called it collision-free quantum money. Now, quantum lightning is just public key quantum money with an extra feature that no generation procedure, not even the honest one, can produce two banknotes with the same serial number, except with negligible probability. So what this means is that not even the bank is able to produce two banknotes with the same serial number. Now notice that in a regular public key quantum money scheme, typically this is not the case. I mean, the bank who creates a banknote can typically create as many copies as it wants of it. Okay, so to make the idea of quantum lightning a bit more concrete, let me give you a sketch in the next slide of a quantum lightning construction. Let H be a collision-resistant hash function. Now, this should also be non-collapsing, but I'll tell you in a moment what this means. Now, the generation procedure is as follows. The first step is to create a uniform superposition over all inputs to the hash function H. Let's say that these x's are n-bit strings. The second step is to compute the hash function H in a second register. And the final step is to measure the second register, the image register. Now let y denote the outcome of this measurement. So condition on obtaining y as an outcome, the first register collapses to a superposition over only pre-images of Y under H. And we'll say that the first register is the quantum banknote, and Y is the serial number. And as you can see, since obtaining a particular outcome Y is a rare probabilistic event, running the same generation procedure again will almost never yield a quantum banknote with the same serial number. And now verification proceeds as follows. The first step takes as input an alleged quantum banknote, computes the hash function H in a second register, measures this register, and checks that the outcome matches the serial number Y. Okay. Now, if a state passes this step with high probability, then this tells us that the state has to be a superposition over pre-images of Y. In fact, a superposition over at least one pre-image of Y. Now, the second step of the verification is to apply a distinguishing algorithm to tell if the first register is in a genuine superposition over pre-images of Y, or if it's just a single pre-image of Y. And such a distinguishing algorithm exists if the hash function is non-collapsing. And this is basically the definition of non-collapsing. And so why is step B important? Well, without step B, an adversary could do the following. The adversary simply picks any x, computes h of x, and outputs cat of x as the banknote with serial number h of x. Okay, of course, knowing x, an adversary can create as many copies as they want of cat of x. Okay? So such a state cannot be allowed to pass verification. And part B enforces that the banknote should be a genuine non-trivial superposition over pre-images. And so what is the intuition as for why it is hard to produce two valid quantum banknotes with the same serial number? Well, if you had two states that are both non-trivial superpositions over pre-images of the same serial number Y, then what you could do is you could simply measure them both, and with noticeable probability, you would get two distinct pre-images of Y. And this breaks the collision resistance property of the hash function. And so to recap, in quantum Lightning, no one can generate two valid banknotes with the same serial number, not even the bank. And this is interesting because it opens to the possibility of potentially removing the trusted third party, because we no longer have to trust the bank not to produce many banknotes with the same serial number, which was a concern before. But however, the question that remains is, how do you prevent people from creating many banknotes with different serial numbers? If there's no banks minting the banknotes, there should be a mechanism that regulates the generation procedure. Okay? And in the rest of the talk, I'll show you how to use quantum Lightning in combination with a classical blockchain to provide such a mechanism. And so to give a further recap before we move on to describing our payment system, I just want to stress that the only con of a blockchain was that it required a consensus mechanism, which inherently takes time. The only con of quantum Lightning was that it requires a bank, a trusted third party. In the rest of the talk, I'll show you how to combine the two to get the best of both worlds, meaning a payment system for which no trusted third party is needed. And payments are still as quick as just sending a quantum state from Alice to Bob. So when Alice pays Bob, no consensus mechanism is required that involves other users. Okay, so how do we regulate the generation of quantum banknotes? First, recall that a smart contract is this very general kind of transaction which allows a user to deposit a number of coins, which can be released according to a set of instructions phi, which are specified by whoever is depositing the coins, by the user himself or herself. Okay, so now to generate a valid quantum banknote in our payment system, a user does the following. So let's say Alice, she starts by generating a fresh quantum Lightning state. And then Alice will deposit some number k of coins, where k is the number of her choice. she'll deposit K coins into a smart contract, and she'll write the serial number S of the freshly created Lightning state in the instructions phi. So the smart contract for this banknote will look something like this. It will say something like, this is a contract for a quantum banknote, the serial number is S, and there are K coins deposited. Now there might be some other instructions as well, as we'll see soon, okay? But we'll refer to such a smart contract with this structure as a quantum banknote contract. So in essence, in order for the quantum banknote to be considered valid, its serial number has to be registered on the blockchain and backed by some coins deposited in the contract. Okay, so we can interpret this as the quantum banknote with serial number S having acquired value K as a result of this process. Now, what about payments? Well, after the serial number S has been recorded in a smart contract, Alice can spend the quantum banknote to Bob by doing the following. She simply sends the banknote state and serial number to Bob, and she also references the quantum banknote contract on the blockchain, which contains S. Okay, and then Bob simply checks the validity of the contract that has been referenced. So it checks that the contract has the right form, it does indeed contain S as a serial number, and then verifies the banknote that he has received by using the verification procedure of the quantum Lightning scheme. Now, if both of these checks pass, then Bob is happy and he considers himself paid. Now, how much has he been paid? Well, recall that the value of the banknote is determined by the number of coins deposited in the contract, in the corresponding contract. So, right, so in some sense, the value of the banknote is backed by the coins in the corresponding contract. So what is the point? What have we gained? Well, the point is that Bob can later spend the banknote to Charlie. Charlie can spend it to Dana, and so on indefinitely, without any new transaction being posted on the blockchain. So crucially, the blockchain is only updated when a new banknote is created, and all subsequent transactions happen off-chain. They don't involve any user other than the payer and the payee. So what we just discussed was a mechanism to generate quantum banknotes, and this was essentially a mechanism to convert classical coins on the blockchain to quantum banknotes. What we'll discuss next is a mechanism to go back, so meaning to convert quantum banknotes back into classical coins. And in order to achieve this, we'll formalize a natural property of a quantum Lightning scheme, which we call Banknote-to-certificate property. And this is what I'll describe in the next slide. So first, recall from our quantum Lightning sketch construction that the banknote state has the following form. It is a uniform superposition over all pre-images that map to some y under the hash function h, and y is the serial number. Now notice that measuring in the standard basis allows to recover one pre-image of y. However, this comes at a cost because it destroys the superposition. In fact, you can imagine that it's hard to possess both a valid pre-image to y and a valid banknote with serial number y. So this is precisely the intuition for the banknote-to-certificate property. And here is an informal definition of this property. We say that a quantum Lightning scheme satisfies the banknote-to-certificate property if there is an efficient procedure that extracts a classical certificate from a valid banknote. Now, this certificate should be efficiently verifiable, given S, and moreover, it should be hard to hold both a valid certificate and a valid banknote with respect to the same serial number. In other words, the certificate acts as a proof of destruction of the banknote, if you will. And we'll use this banknote-to-certificate property to go from quantum banknotes back to classical coins. So here's how we'll do it. It's pretty simple. So we'll add another rule to the set of instructions specifying our quantum banknote smart contract. And this new rule says that anyone who posts a valid certificate with respect to S, where S is the serial number contained in the contract, can recover the deposited coins. So very simply, what Alice does if she wants to get rid of the quantum banknote and recover its value in coins is that she will extract the classical certificate, call it C. This destroys the state, but she's able to post C to the blockchain and recover the coins in the contract in a future transaction. Now, here are some practical considerations about the mechanism that I just described. Now, in an idealized model, in which transactions appear on the blockchain in the order that they are submitted by users, it is somewhat straightforward to prove some formal security of our payment system and the two mechanisms that I described. And this is indeed what we do in our paper. In practice, however, a malicious agent who controls many users could succeed at delaying certain messages from appearing on the blockchain and speeding up others, favoring other messages. So here is a possible practical attack on our payment system. The malicious agent can simply wait for an honest user to broadcast a valid certificate. For example, if the user wants to convert her quantum banknote back to coins, and the malicious agent steals this certificate while the transaction is still in the pool of pending transactions, and goes ahead and posts its own transaction first, containing the certificate on the blockchain, and thus recovers the coins in the corresponding contract. Now, there are a couple of ways to deal with this issue. In the next slide, I'll tell you about one of them. So we resolved this practical issue, although unfortunately, because the time is limited, I won't show you exactly how. We solve it though by formalizing a novel property of a quantum Lightning scheme, which could be of independent interest. We call this property banknote-to-signature property. It is a strengthening of the banknote-to-certificate property, which we discussed earlier. And it's a strengthening in the sense that one is not only able to extract a classical certificate from a valid quantum banknote, but one can also extract a signature of any message they want. And again, producing this signature destroys the quantum state. So here's a depiction, right? For the banknote-to-certificate property, recall that you destroy the state to obtain a classical certificate in exchange of a classical certificate. For the banknote-to-signature property, you also get to input a message M. Now you still destroy the state, but what you obtain is a signature of M, which is efficiently verifiable given S. And what we show in our work is that any quantum Lightning scheme that satisfies the banknote-to-certificate property also implies a quantum Lightning scheme which satisfies the stronger banknote-to-signature property. And we give an explicit construction. Now, it should be quite natural to see how this property can be used to resolve the practical issue that we were discussing earlier. So instead of broadcasting her certificate in the clear, which could lead to it being stolen, Alice instead uses the banknote-to-signature property. So instead, she broadcasts a signature with respect to serial number S of the message. For example, Alice wishes to convert her banknote back to coins. And now, of course, the attack that we mentioned earlier of a malicious agent stealing a certificate is no longer possible because a certificate is never broadcasted in the first place. And moreover, the malicious agent cannot possibly produce a signature with respect to serial number S of any message other than this particular one here, which contains Alice's name. So I want to end the talk with a brief comparison of our payment system to some classical alternatives and with some disclaimers. So first of all, the idea of transactions happening off-chain has already been explored classically. And there are some proposed solutions, notably the Lightning Network of Bitcoin. And interestingly, the name Lightning Network has nothing to do with quantum Lightning, and the Raiden Network on Ethereum. So the main pro of these solutions is that they don't require quantum technologies that are far into the future. Now, one of the cons is that although most payments are not recorded on the blockchain, so they happen off-chain, these payments still involve many parties, other than just the payer and the payee. And hence, inevitably, they require transaction fees. Now, there are some other practical constraints to these solutions that I won't discuss here, but you can ask me about them. And now, finally, I just want to emphasize that we don't actually currently know of a quantum lightning construction that is secure under standard assumptions. And of course, the payment system that I described hinges on the existence of one. So we have a concrete construction by Zandri that is secure under some non-standard assumption. So it is indeed, in my opinion, a very interesting problem to try to come up with a construction from standard assumptions. So this is all that I wanted to say. Thank you very much for listening.